Hey, hello, workshop students. I thought I'd try to answer some questions by video. Let's see. Looks like you guys sent me a couple questions here on the quiz. So let me start. I think this is number 3. So what should I call this? Weekly quiz number 3. I guess this would be on energy, maybe work energy. All right, well, I'll start there because there was one on number 3, one on number 5, and the one I'm not sure about doesn't seem to have a number here, but this one here. So I'll do those 3, and I'll break them up into 3 sections. So let me start here. It says a 1 kilogram box is resting on a table. A person then pushes it horizontally with a constant force of 44.9 newtons for a distance of 1 meter. The box has a final speed of 6.15 meters per second. The work done by friction during this time is blank joules. Note, express your answer as a negative. So I like to say, remember the principle of conservation of energy. It's a nice principle that simply says if you have an isolated object or objects, the energy you start with equals the energy you end with. And so there's the math behind it. Now, if it's not isolated, then you could add energy by work. Okay, and so we could say you put some energy in, plus whatever you start with is what you end with. All these conservational principles you could kind of just think of like a checking account, an accounting game. You know, you start the month with this much, you put this much in or take that much out. So this could be positive or negative, and then this is what you end with. And so starting and then plus or minus the work equals what you finish with. So it would look something like this. You would say, okay, I could start with some initial kinetic energy. I could start with some initial gravitational potential energy. I could start with some initial elastic energy from a spring, plus any work that's done, then equals the final energy. And so this would be the final speed. This could be related, to the final height, and then also the final position of the spring. So this is the more general equation. This is including the kind of the 4 energies you will work with, and I'll call this work by friction. But it could be some other additional energy added as we get to other problems. I guess what I'm trying to say here at the beginning is think about all the 4 energies you're working with. Everything will fall into that place. You will have either kinetic energy, gravitational potential energy, a spring energy, I like to call it an elastic energy, and then a work done by friction. Sometimes we call that heat, so the negative of the work is the heat, and so a thermal energy, I'll put it on that side to make it positive. But again, then these 3 energies. So these are the 3 main energies, plus the work done by friction. This is our principle of conservation of energy. And you could pretty much sum up the whole chapter that way. So let me apply this idea to this problem, because on this particular problem, we have a 1 kilogram block at rest. And so the first thing I would do is to say 0 kinetic energy at the beginning. Now later on here, it says it's pushed on a horizontal table. So that would mean this term and this term don't change. The height doesn't increase or decrease. Maybe it's just easier to call it height 0, and so that term and that term is 0. Although you might feel more comfortable calling the ground 0. Okay, so then the height of the table might be somewhere near 1 meter. But either way, these 2 are going to cancel off. And so this problem does not involve that term. There is no change in height, so we won't need to worry about that one. And then likewise, as you read this question, there really is no springs involved. And so even just talking about this equation is kind of difficult because there is no spring. And so I'll just, cancel that one off. All right. And so what it's boiled down to is the work then is equal to the kinetic energy. By the way, you probably know this better as if I would have taken this term and moved it to the other side. You called this the work energy theorem. Now, you would have said, hey, the work done is equal to the change in the kinetic energy. That's what this statement here is saying. So whether you want to begin with what I call the principle of conservation of energy, where I just take all the energies and set them equal, or if you want to start with the work energy theorem, they're saying the same thing, of course. All right. So I hope I'm not blabbing too much, but hopefully that's helpful. So jumping into this problem during a quiz, I would say maybe the best thing is to start with your thinking of the work energy theorem or this one. Either way, what you have is work is equal to 1/2 mv final squared, since there is no initial. And if you grab a calculator to get a number here, you will have this 1/2, what was the mass here, times 1 times a speed of 6.15 squared. Okay, so this is going to be 18.9 joules. And the real, I don't know if trick is the right word, but the main idea of this problem is that there is work done twice, by two causes, I guess I should say, is because some of the work comes from a push. And so when I say the integral of f dot dr, I can say that force is made up of a push and, maybe I should have put here net force, okay. But that net force is a push, but it's also a force of friction. And that has to equal the 18.9, okay? And this one is pretty easy to do. Well, they're both kind of easy to do. They look hard because they're an integral, but when you have an integral that you have a constant, this just boils down, this dot product would be the magnitude of the push, integrated the distance traveled, and if you're pushing it in the direction it moves, if a person then pushes horizontally with a constant force a distance of 1 meter, when you do this dot product, you get cosine of 0 degrees. Because remember, this angle is the angle between these two. And so these two as a vector here are what direction do you push it and what direction does it move. And this tends to imply they're going the same direction, so there's zero angle between them. Whereas this one, this is the force of friction. And actually, I don't even know if I should even do the dot product here, because this whole term right here is what the question's after. It's after how much work is done by friction. So it's this term that it's after. I was tempted to kind of do the dot product and point out that the angle would be 180 degrees. So you'd have cosine of 180 degrees, which is why this will come out to be negative, since cosine of 180 degrees is a negative number. And that's why it says, you know, this is going to come out to be a negative number. Express your answer as a negative number. Okay. So let me just solve for this whole box. I'm not going to actually do the integration. Okay. So this would be this term, which since the push is a constant, I would just have force times the distance it traveled. Let me put d. And then plus, and in this box, let me just put the work by friction. And that equals to 18.9. Coming back to this problem, the push is the 44.9 newtons times the distance of 1 meter. And so this work by friction, then I can solve for. And so it would be this 18.9, and then I would subtract the 44.9 and get a negative 25.9, I got to round it up here, 26.0. So 26.0 joules would be the work done by the friction. All right, well, I hope I didn't have to bore you too much by going into some detail here, because it probably shouldn't have taken quite that long to explain, but it really is just right here. This right here, this, which comes out to be 18.9, is equal to nothing more than the two works, the work done by the push and the work done by friction. So you know that one because of this, and you know that one because of this, and the one you don't know, you're solving for. All right, hope that's helpful to somebody. Take care.